Hello everyone and welcome back to another video. Today we'll be taking a look at a British Informatics Olympiad question, and we'll be taking a look at the third question from the 2015 paper. So let's have a quick look at the question. Pretty much, I'll let you have a quick read of the question before I explain it on the whiteboard as well as the solution. Okay, so the main essence of how this question works is that we need to, let's say we have a number, 17, and we have a target number. Let's just pick 7, for example, like any random number. We need to take a path such that all the numbers within that path, within all of these paths, these lead to further paths. Or we need to find such a path that it leads to a direct path with 7, through which we only traverse through prime numbers, and the difference of which is a power of 2, basically. So, like as you may have noticed, I went into the graphical approach quite quickly. So, we'll be referring to these numbers as nodes, and then all neighbors as possible nodes as well. And you'll see why this is very helpful way to think about it in the future. So, pretty much from 17, we can basically make journeys from either plus minus 2, plus minus 4, plus minus 8, as long as they are prime. So let's just think about any numbers which are a distance of 2 away from 17. So we have 15 and 19. 15 is not prime, so 19 is the only valid one. So we have 19 over here. Now distance of 4, 21 and 13. 13 is prime, but 21 is not. So we'll just put 13 over here. Distance of 8, we have 9 and then 17 plus 8, which is 25. Neither of which are prime. Distance of 16, we have 1 and 33, neither of which is prime. So these are the only two possible ways in which we can go from 17. So now I'll probably need a bit more space, but let's just erase this for now. Now our target is 7, so we consider all possible ones leading from 13. So 11 would be one of them. Again, 17 would be one of them from 13, but then that's where we came from. So there's no point visiting 17 again. So just to keep track, we'll have some sort of visited array. So we have 17, 13, and 19, which are all part of that visited array. And now we have 11 as well, also part of that visited array, since 11 is part of our graph. Now, if a particular element is within this array, then there's no point visiting it again. So now, from 13, any other numbers which we would have plus minus 8, so we would also have 5. So now we can append 5 into our visited array. And now from 19, we'll also have 11 as one of the numbers. And then we'll have a few more for each of these. But I'm sure you get the idea. We pretty much just continue all of these on. And then the way we would get the answer is from 11, we would get to 7. And then this would be the shortest path, since it would be of length 3 and would reach our target. So as soon as we've reached the target, we can stop our search. So if you're familiar with breadth first search, this is exactly what it is. We start from a particular node, we explore all its neighbors, and then we repeat the process for each of those neighbors, exploring all of its neighbors, etc., etc. And breadth first search, or BFS for short, is very, very handy in finding shortest path between two nodes. So in this case, it will give us the shortest path between 17 and 7. Now let's just consider how would we implement this with code. So the first thing which we would need to do is, we pretty much just for finding the prime numbers, we kind of know the first 20 prime numbers on top of our head, but then a computer clearly wouldn't. So we would need to maintain some sort of array which maintains the first, let's say, n prime numbers, where n is the number which, n is our limit, the largest number which we can have. So just to be safe, we can include any prime number less than n. So we should have all prime numbers less than n inside our array, just so we know exactly which numbers we have a choice from. And then from there, it's quite simple, since all we need to do is check plus minus 2, plus minus 4, plus minus 8, etc., etc. And then we need to check if those numbers are prime, then we would need to append them inside our BFS like data structure, and then as long as those numbers haven't been visited earlier, we are free to visit them, and then we just continue expanding our tree until we reach a certain number, let's say 7, which is our target number. So that's pretty much how we will execute this code. Now let's have a quick look at the program which we used for this code. So we pretty much have this deck data structure, which is very, very useful in Python for conducting BFSs, since it's basically a double-ended queue. How it works is you can pop elements from either end, and you can append elements from either end. So it's very handy for doing BFS, since you can append elements to the end and pop elements from the start, and also for 0-1 BFS, but we'll come to that in another video. And now these basically take the 3 inputs required: maxi, num, and required. So maxi is the maximum number which we are allowed to have. The reason why I didn't choose max is because max is a built-in function in Python. We don't want to confuse ourselves. We have num as well, where num is the first element which we have in our particular BFS, and required. Required is the target element. So, and now we also have the sieve thing. If you're not familiar, this is the Sieve of Eratosthenes. I'll quickly explain on the whiteboard, but feel free to skip ahead by a couple of minutes if you're already familiar with this. Pretty much, how the Sieve of Eratosthenes works is that we have, let's just consider we have a certain array, which have all the numbers, all the first, like, let's say 10,000 numbers, then we just choose any arbitrarily large number. We have all of these. Now, the way the Sieve of Eratosthenes works is this gives us all the prime numbers. So how do we determine this? So let's just ignore 1, since 1 is a special case, but let's just go from 2 onwards. So we initialize all the elements to being prime initially, since we don't know whether they have any divisors. So I'll just be referring to them as true, true being the number is prime, and then false being the number is not prime. So true, true, and true. Okay, and now let's just ignore 1 from our search, since if we were to include 1, it would just mess up everything up. So since the number 2 already has a true label, we know that no number before 2 can be divisible by 2. Like it is divisible. Or it is a divisor of 2, sorry. So therefore 2 must be prime. Hence we can move our search to the next element. So now we go to 3. Likewise for 3, there's no number less than 3, which is divisible by 3. Hence 3 is also prime. But now, when we go to 2 and 3, what we need to do for these numbers is we need to go to all possible, all of the multiples of 2, and then make them false, since we know that they cannot possibly be prime. So for 2, we go to 4, 4 we go to 6, 6 we go to 8, etc., increments of 2. Then we mark all of these numbers as not prime. So I'll just cross them out for ease. But we know that 4 can't be prime, 6 can't be prime, 8 can't be prime, since they're all divisible by 2. And now we have to apply the same logic with 3. So with 3, we know that all multiples of 3 cannot be prime. So then we would cross 6 out again, it's already crossed out, then 9, 12, so on. And now 2 and 3 are prime. Now 4 we skip, since we know that 4 is not prime. Now 5, since it hasn't been crossed out, we know that has to be prime. But then we cross out all multiples of 5, so like 10 would get crossed out, etc., etc. And then if we repeat this, we'll basically be left with all the prime numbers. And then the beauty of this is that they'll all be stored in an array, and then it will be marked with true or false whether the number is prime or not. So then that can be a quick, easy way to determine whether a number is prime. We'll just refer to its index in the array, and if that's true, then we know the number is prime. If it's false, we know the number is not prime. So now let's go back to the program. So this is basically the sieve which we have over here. This bit of code is just executing exactly what I just told you. We go in increments, and then we go to the maximum plus 5, The reason for this is just so, we don't want to just go to the maximum element, since we might have like some off by 1 errors or something, so we just go a few elements above just to be safe. And we set the number to be false, so like pretty much exactly how I described it. Then just to test whether a number is prime or not. Now we also have this thing called visited. We'll come to this visited later, but what this visited is it's basically like a sort of array which keeps track of whether an element has been visited or not in our BFS search. Exactly how I was doing earlier, since if a number's already been visited, there's no point visiting it again, since we've already visited all of its neighbors. So now we have this queue structure, which is from the deck, and we initially append num and 1. So this queue will be made up of tuples and lists, and then all of these lists will have two particular values. One of the values will be the number which it has. Let's say the prime number which it has, let's say like 10 or whatever, 11 or 13, 17, whatever. And the second particular element which it will have inside the list is the number of operations which it took to get to that number. So initially we have 17. So it took 1 operation to reach 17, right? And then it would take 2 operations to reach 13, since 17 minus 4 would give 13. And then etc, etc. This basically just keeps track of how many iterations there have been. And the reason why we start with 1 and not 0, since you might be thinking that 17 technically would require 0 operations to get to 17, since that's why we started. The reason why is just so we can print that number straight off. We could have done 1, but then over here we would have to print L1 plus 1. It's a very minor detail, don't worry about it. So now we pretty much just implement the BFS. So we pop the first element from the queue. L0 would basically be the number of which we have, and L1 would be the counter of the number of operations required to get to that number. And now what this particular bit of code does is we go to all possible powers of 2, which are less than or greater than that particular number. So over here, this is the logical shift. This is basically a bitwise operator for LSL of LSL, like logical shift rights, logical shift lefts. So what they do is 1 logically shifted 3 spaces left would increase it to the power of 3. So it would be 1 times 2 to the 3, which is 8. So what this does is it'll basically provide all possible numbers which are plus minus 2 to the I elements less than or greater than L. So where L is the element over here. Excuse me. So now all we need to do is check whether these particular numbers, n1, are within the limit, i.e. less than max c, and also whether they are prime, and if they're not visited. If it satisfies all of these, then we append that to the particular element. We append, or we could just replace this with n1, it's basically equivalent. Maybe I'll just do that just for, just to make it a bit easier to read. But we pretty much just append that particular number, and then we also increment the number of operations to that number by 1. Since in doing so, in doing this particular operation, we've increased the number of operations by 1. And then we also mark the visited of that number to be true, so we won't accidentally visit it again. And we also do this for the second number being the number which is less than that particular number, the first number being the one which is greater than, the second number being less than. And we just repeat this BFS code for all possible numbers, and that will pretty much be it. So pretty much what we need to do is we need to check whether these numbers n1 and n2 are within the limit, i.e. whether they are greater than 2, which is the smallest possible prime number they could be, or less than max c, which is the highest possible number they can be as well, and whether these are prime, so i.e. whether within our sieve that they are true, and also whether they are not already visited. If all 3 of these conditions are met, then we can append that into our BFS queue, and then mark that as visited, and then we just repeat. So that's pretty much it for this code. Now let's just see if it works on some of the test cases. let's just quickly test it. Okay, let's just test it on this one maybe. Oh, so sorry, I was running a different program, but as you can see over here, 16 outputted in like just under a second, so that's nice. Now, if we test another one, if we go here, maybe, and now go back. This also outputted 18 in under a second. So yeah, that's pretty much it for this video. I really hope you enjoyed watching. Hopefully you learned something new. There was quite a lot going on in that particular program. Hopefully you enjoyed it, and if you did, please be sure to leave a like and subscribe, and I hope to see you in another video next time. Thanks for watching. Bye.